The James Webb Space Telescope, or JWST, is living up to the hype and its price tag by revolutionizing our understanding of the universe. Most recently, the Supreme Observatory has just stunned the whole world with its first triple image of supernova captured in a variety of invisible to human wavelengths, revealing some absolutely riveting corners of the cosmos. What's more interesting is the extraordinary discovery might be the key to resolving astronomy's greatest modern puzzle. Join us today as we dig deep into the James Webb's first triple-image supernova that could simply break the law of physics. One of the biggest problems facing modern astronomers, astrophysicists, and cosmologists, every scientist who studies the universe itself for a living, is that we do not understand how quickly the universe is expanding. The most direct method of measuring the expansion rate, by looking at more and more distant objects and tracking how quickly they appear and recede from us, consistently gives answers that are about 9% higher than the values we get from looking at signals imprinted in the very early universe. This has led many to question whether there's a crisis in cosmology, and if we need to overhaul our entire way of looking at the universe. One potential solution could lie in directly measuring large numbers of objects whose intrinsic properties are known, so-called standard candles like Type 1a supernovae, at even greater distances. A huge challenge to this has been that supernovae are rare, infrequent, and very difficult to observe in extreme distances. Even with its unprecedented powerful eyes, JWST, with its narrow field of view, will only observe these events rarely. However, a new proof of concept has just arrived. In a new paper just submitted on September the 13th, 2023, Dr. Brenda Fry and her collaborators spotted a Type 1a supernovae that appeared in triple, magnified and distorted by the gravity of a foreground galaxy cluster. It just might be the key to measuring, to greater precision and accuracy than ever before, exactly how the universe truly is expanding. Type 1a supernovae are one of the most important classes of astronomical objects in the entire universe. They have a rare combination of traits that make them incredibly useful. They're very bright objects, meaning that we can not only observe them in nearby galaxies, but in galaxies billions or even 10+ billion light-years away. They're incredibly standard, meaning that if you measure how they brighten, reach their peak brightness, and then fade over time, you can infer how intrinsically bright and luminous they were. They're slowly evolving transient events, meaning that even if you measure them at just a few time intervals, even if those measurements are separated by weeks, you can reconstruct their intrinsic properties. And they stick out like a sore thumb. They are practically no imposter events that risk being confused with Type 1a supernovae. If you can measure a Type 1a supernova's light over time, what we call its light curve, you can learn how far away from you it is. If you then tie that supernova to the host galaxy where it occurred, and then measure the redshift of that host galaxy, you can use them to measure the expansion rate directly. They're truly remarkable objects. However, there's something that's even more exciting. Sometimes you'll have a galaxy whose light is distorted into multiple images by the presence of a foreground mass, also known as a gravitational lens. The more massive the foreground object is, the greater the strength of the gravitational lens, and the greater the background volume of space that will be potentially magnified by this lensing effect. And if you're very lucky, that lensed galaxy will be massive, forming lots of new stars, and will be a hotbed for cataclysmic explosions that accompany a star at the end of its life cycle, the various types of supernovae. Back in the early 2000s, many astronomers recognized that if you could successfully map out the mass profile of a gravitational lens, i.e. if you could understand how the foreground mass was distributed to cause the multiply lensed images of the background object, you could use the measurements of the gravitational time delay of any transient events that occurred within them to measure how quickly the universe is expanding. Because Type 1a supernovae are such good standard candles, they possess a unique power, You can measure the magnification power of the gravitational lens directly, and then use that to measure the expansion rate to alarmingly good accuracy. That piece of information alone is enough to give us a big dream to strive for in astronomy. If we can find a strong, massive foreground gravitational lens that magnifies a region or multiple regions containing lots of galaxies or even a galaxy group cluster where the background lensed galaxies exhibit multiple images, are very distant and at a high redshift, and also are massive and star-forming, then we should be able to observe it periodically, over long periods of time, and may detect one or even large numbers of supernovae, including type 1 supernovae, that we can use as standard candles to measure how the universe is expanding with greater precision and accuracy than ever before. All of that combined is why this new paper is so remarkable. While performing near-cam imaging of a massive galaxy cluster, one where gravitational lensing effects like extended arcs, multiple images, and distorted galaxy shapes are clearly visible, astronomers caught evidence for a type 1a supernovae occurring in one of the background objects. The supernova appeared in 3 independent places in the image, and just happens to be the second most distant type 1a supernova ever observed, behind only 2013's S.N. Wilson. First off, the foreground galaxy cluster, i.e. the one doing the gravitational lensing, is a pretty big one, known as Galaxy Cluster PLCK G165.7 plus 67.0, or G165 for short. It has a total cluster mass of about 260 trillion. That's 2.6 times 1014 solar masses, or a few hundred times the mass of the Milky Way. This foreground cluster, G165, is already an impressive 4.5 billion light-years away and contains 2 main clumps of mass near the center of the cluster core, with several other groups of galaxies located within the greater cluster as well. The enormous arc located around the edge of the larger clump, named Arc 2, in typical astronomy fashion, actually consists of 3 separate images, all blended together, of a background galaxy that's much farther away, some 16 billion light-years distant from us. It's that galaxy, known as Arc 2, that's the host of the Super 1a supernova that was observed. 3 rounds of observations were taken of this object. 1 round on March the 30th, 2023, spanning 8 different near-cam filters. 1 round on April the 22nd, 2023, spanning 6 different near-cam filters, and 1 more round on May the 9th, 2023, spanning those same 6 near-cam filters. It was through examining these sets of images that the transient event of a Type 1a supernova was able to be extracted from the data. But this arc was not the only interesting feature to be captured by JWST. It turns out that over the entire field that was imaged by the observatory, a remarkable 21 objects were found exhibiting what's called image multiplicity, meaning that there are multiple images available of at least 21 foreground, gravitationally lensed objects in this field of view. Some of them were located very far from Arc 2, but a significant number of them were nearly coincident in space, occurring in the same region, at least visually, as where Arc 2 and the triply lensed supernova was located. Even more remarkably, JWST's primary instrument for performing spectroscopy, NIRSPEC, was used to take the spectrum of many of those nearby lensed galaxies. Were these just galaxies at very different distances that happened to be along the same precise line of sight as Arc 2, or are they actually indicating a group of clusters of galaxies? With NIRSPEC, we can find out. If the galaxies are simply along the same line of sight, but aren't clustered together in space, they'll likely exhibit key atomic and ionized features, emission and absorption lines, very different wavelengths. But if they all have the same wavelength but different line intensities, that would indicate a galaxy overdensity, a group or even a cluster of background galaxies, all lensed and magnified by the foreground cluster. As you can see from the NIRSPEC data above, the elemental signatures are unambiguous. there are a significant number of galaxies whose light is all shifted by the expansion of the universe by the same amount. There are at least 6 member galaxies in this group, and 4 of them are incredibly close together, within only a few 100,000 light-years, or about the diameter of the Milky Way, of one another. However, it's the host galaxy, Arc-2, where the supernova is only 5 to 7,000 light-years from Arc-2 itself. That's by far the most massive galaxy found in this overdense clump. Elsewhere in the field of cluster G165 are 2 other galaxy overdensities, shown below. One of them is located slightly closer than the Arc-2 clump, at a distance of about 15 billion light-years, while one is even more distant, somewhere between 18.1 and 18.3 billion light-years away. It is unknown whether this latter set represents 2 very nearby but unrelated clumps, or whether they're all part of one even larger cluster of galaxies. In either case, we've learned that G165 is remarkable in another sense, that not only does it house a triply lensed supernova, and the second farthest Type 1a supernova ever discovered, but that the region of space behind it contains at least 3 separate groups or clusters of galaxies, that the main cluster itself is gravitationally lensing. These are 2 more pieces of important science that come out of this remarkable study. One of them is that, based on this exquisite gravitational lensing data, we can now reconstruct the lensing profile of the foreground galaxy cluster, enabling us to both model the mass distribution of the foreground cluster and also to infer where the regions of maximum magnification are occurring. In the search for ultra-distant, faint objects, it's vital to understand exactly how much magnification is occurring and where that magnification is taking place. Otherwise, it's possible for us to bias ourselves towards a wrong answer. But even more importantly, the better we can model the mass distribution and the better we can understand the lensing magnification of the background objects, the more successful we're going to be at using the time delays of any multiply-imaged transients, such as Type 1a supernovae, to attempt to infer the expansion of the universe. There's a reason that the triply lensed supernova was given the name Supernova HOPE, or SN HOPE for short. It gives us hope that we'll be able to better measure the Hubble expansion rate, HO, to better accuracy than ever before by using this technique and maybe even this particular lensed system. At the last piece of important science to come out of this work is not to be understated. All of the background lensed galaxies that had their spectra taken can have their star formation rates determined. In each of these galaxies, there's a transition of hydrogen that's very easy to measure, the Balmer alpha line, sometimes just called HA, which represents the n equals 3 to n equals 2 transition of electrons within the hydrogen atom. In the laboratory, this makes a nice red emission line of wavelength 656.3 nanometers, and in these distant galaxies, you simply multiply that number by the stretch factor of 1 plus redshift to find that line again. As long as you correct for stellar absorption, absorption by stars, dust extinction, light blocked by intervening dust, and slit losses, an instrumental effect, you can measure the star formation rate and infer the expected frequency of supernovae you'll see with continued monitoring. What they found is that on the opposite side of the cluster G165, i.e. on the Arc-1 side instead of the Arc-2 side, they anticipate an expected supernova rate of about 1 per year. Even though Type 2 supernovae are more common than Type 1 supernovae, it's possible that continued observations of this galaxy cluster will yield several additional Type 1a supernovae over the lifetime of the James Webb Space Telescope. It's important to note that this is not the first triply lensed supernova that JWST has seen. That honor belongs to the galaxy cluster RxJ2129, whose data was released back at the end of February. However, only the faded remnant of this transient existed in one of these images, and it's far less distant than the supernova seen in Arc-2 of galaxy cluster G165. Instead, in this new system, We now have a triply lensed supernova, at least 3 independent background lensed galaxy groups, and a very solid, data-driven lensing magnification map of the entire galaxy cluster. With further observations, and as more time passes, both from new data and from data that's still being analyzed and prepared by this collaboration, we may obtain the most precise and accurate measurement for the expansion rate of the universe using the cosmic distant ladder method of all time. This triply imaged supernova was not named Supernova Hope again in vain, as it really does give us hope that the answer to today's greatest cosmic puzzle may indeed be written on the face of the universe. With JWST going strong, we may have already found the galaxy cluster and the gravitationally lensed system that will resolve what's been puzzling astronomers for the entirety of the 21st century. As NASA's time machine continues to make shocking discoveries that could change cosmology, the agency also recently completed a historic mission for the United States. In a mid-morning operation at the U.S. Army's Dugway Proving Ground in the arid Utah desert, teams with NASA and the U.S. Air Force successfully recovered a space capsule with samples of asteroid Bennu, taken by the agency's OSIRIS-REx spacecraft in 2020. The mission marks the first time that NASA has taken a sample of an asteroid, not to mention successfully recovering it. After traveling for over 4 billion miles, 6.2 billion kilometers that is, to reach Bennu and then make the journey home, the OSIRIS-REx probe released its sample return capsule this morning, while it was about 63,000 miles or 101,000 kilometers above Earth. The capsule contains some 250 grams or 8.8 ounces of rock and other material from Bennu, material that could help answer some of scientists' most burning questions about the origins of life on Earth and the early days of our solar system. Touchdown for science. For the first time in history, we brought goodies back home from this kind of object. This is so huge and we're all breathing a big sigh of relief, said Jim Garvin, chief scientist of NASA's Goddard Space Flight Center, from the landing site during a live broadcast. The OSIRIS-REx capsule reached speeds up to 27,000 miles per hour, that's over 43,000 kilometers per hour, and its heat shield experienced temperatures as high as 5,300 degrees Fahrenheit or 2,900 degrees Celsius as it descended through Earth's atmosphere. The capsule deployed its main parachute at an altitude of about 20,000 feet, 4 times higher than expected at 5,000 feet, but it appeared to land safely. Officials with NASA and Lockheed Martin Space Systems, which built OSIRIS-REx, told reporters in the post-landing conference that drogue chute likely deployed, but was just not seen on cameras monitoring the descent. The bottom line is, we landed, Mike Moreau said. When the main parachute came out, that was the moment I was waiting for. Mike Moreau was the OSIRIS-REx recovery team lead and NASA's Goddard Space Flight Center member, and he said this in a debriefing soon after the capsule landed down. The drogue's on top of the main parachute, so all had to come out, he added. As the sample return capsule floated down to the desert floor of the U.S. Department of Defense's Utah Test and Training Range here in Utah, the capsule cooled down enough so that the U.S. Air Force personnel could approach it after locating it. The descent from the edge of the atmosphere to the desert sands took under 10 minutes in total to end a 4 billion-mile journey. The $1 billion OSIRIS-REx mission launched in 2016, arrived at Bennu in 2018, and collected samples of the asteroid in 2020. Boy, we did stick the landing, Dante Loretta, principal investigator of the OSIRIS-REx mission, said in a post-landing debriefing. Once on the ground, the capsule and surrounding area was examined to make sure it was safe for OSIRIS-REx team members and recovery personnel to approach and examine the capsule. An early examination by recovery teams found that the capsule was intact and suffered no breaches during landing. From there, the capsule was hooked up to a helicopter via a long line and airlifted to a temporary clean room set up by the U.S. Army's Dugway Proving Ground. Once secure inside the facility, the capsule was opened, and the canister inside that contains the precious sample of asteroid Bennu will be prepared for transport once again. The asteroid material will next be loaded onto an aircraft and flown to NASA's Johnson Space Center, or JSC, in Houston, Texas, where a newly built facility is waiting for it, the agency's Astromaterials Research and Exploration Science, or ARES division. Congratulations to the entire OSIRIS-REx team. You did it, NASA Administrator Bill Nelson said in a video during a live commentary. This mission proves that NASA does big things, things that inspire us, things that unite us, things that show us that nothing is beyond our reach. From there, the sample will be divided up among different scientific institutions and world space agencies. NASA will keep 70% of the sample at JSC, where it will analyze it for years to come. Another 25% will be shared between over 200 scientists at 35 different facilities around the world. 4% will be given to the Canadian Space Agency, and another 0.05 will be given to the Japanese Aerospace Exploration Agency, or JAXA. OSIRIS-REx is NASA's first to collect an asteroid sample, but JAXA has 2 such missions under its belt. That agency's Hayabusa 1 collected materials from asteroid Itokawa and returned them in 2010, and Hayabusa 2 returned samples of asteroid Ryugu in 2020. The successful landing and recovery of the asteroid Bennu samples marks the end of a 7-year mission that saw its share of surprises. When the spacecraft arrived at Bennu in 2018, it found an asteroid resembling more of a pile of gravel and rubble than a solid rock. Scientists with the mission then had to rethink the plan for the probe's landing, which required reprogramming the spacecraft to land in an area less than a quarter of the size of its original intended landing site. But the OSIRIS-REx team pulled it off. Loretta said during a pre-landing media briefing on September the 22nd that the OSIRIS-REx team has been consistent in its ability to work through the unexpected issues that pop up. We've always taken a deliberate, careful, cautious approach, Loretta said, and I think that's why this mission has been so successful up to this date. And because it's been so successful, scientists will analyze the rocks and soil from Bennu over the next 2 years. According to Lori Glaze, director for NASA's Planetary Sciences Division, certain steps leading to this highly anticipated analysis will possibly be delayed, but the sample will remain protected and safe despite any disruptions to the schedule The sample has waited for more than 4 billion years for humans to study it, and if it takes us a little longer, I think we'll be okay, she said. Along with a previously returned sample of the asteroid Ryugu from Japan's Hayabusa 2 mission, the rocks and soil could reveal key information about the beginning of our solar system. Scientists believe that carbonaceous asteroids such as Bennu crashed into Earth early during the planet's formation, delivering elements like water. Scientists believe that the asteroid Bennu is representative of the solar system's own oldest materials forged in large dying stars and supernova explosions. And for this reason, NASA is investing in these missions devoted to small bodies to increase our understanding of how our solar system formed and how it evolved, Glaze said. But the sample can also provide insights into Bennu, which has a chance of colliding with Earth in the future. It's crucial to understand more about the population of near-Earth asteroids that may be on an eventual collision course with our planet. A better grasp of their composition and orbits is key to predicting which asteroids may have the closest approaches to Earth and when, and essential to developing methods of deflecting these asteroids based on their composition. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content like this and to always improve. And as always, thanks for watching, and we'll see you next time.